Good. So our next speaker is Giuseppe Leoncini from Maverick University and University of Milan that is going to talk about enriched homotopy cocompletions whenever you're ready.
Okay. So first of all, thank you very much to the organizers for inviting me to talk and also for organizing this project and maintaining it. So I'm very happy to be speaking here. I'll be speaking about enriched homotopy cocompletions. So this is a project that essentially started just from my attempt at understanding homotopy colimits, because there are many ways to compute homotopy colimits. And so I just wanted to have a conceptual understanding of homotopy colimits, and this is how I was motivated for this project. So, so you know that colimits, you can generalize ordinary colimits in two directions, the homotopical one and the enriched one. And I would like to understand how to find a common generalization. And I have some requirements. So the first requirement is that I want to retrieve homotopy colimits over the base given by sets, not simplicial sets, because you don't need simplicial enrichment to have homotopy colimits. So I want to retrieve the most general way to compute homotopy colimits, not just over simplicial sets. Then the second requirement is that I want to retrieve weighted colimits, enriched colimits, ordinary enriched colimits, when I consider categories where the weak equivalences are isomorphisms. And of course, if I take the intersection of these two requirements, I want to get just ordinary colimits. So whether these are natural requirements or not, I think they are. It's up to you to judge. So let me say that there is another way to think of enriched homotopy colimits, which is in some sense more traditional, which is to instead fix an homotopy theory on the base V. And this is also something natural to do, because when you do enriched homotopy theory, you want to enrich in an homotopy theory. You don't want to enrich just in a one category. So in some sense, I would like to reconcile these requirements with this other point of view on enriched homotopy colimits, and I will speak about it at the end of the talk. But I just want to say that if you take V to be simplicial sets with Quillen model structure, and you consider homotopy colimits enriched in Quillen model structure on simplicial sets, you do not retrieve all homotopy colimits. You just retrieve, for example, homotopy colimits in simplicial model categories. But simplicial model categories are much less general than co-complete infinity categories. So you don't get all co-complete infinity categories. So what is the spoiler of the talk is that the approach that I want to take is to consider simplicial objects in V, and then there will be some homotopy theory which will play the role of the homotopy theory of spaces. So let me recall what homotopy colimits are. The most basic thing that one hears is that they are the derived functor of the colimit functor. And this is a good way to compute them, but it cannot be a definition because you are assuming that colimits already exist. So here I will not give a definition of homotopy colimits. I want to think of what they should do. So one way to think of them is that they are one categorical models for infinity categorical colimits. And another way to think of them is that you have categories which have additional structure, which is just a class of maps, and you want your gluing to be coherent with respect to this choice of structure that you have. And in some sense, this second point, I think, is more fundamental because, for instance, for whatever model of infinity categories you have, you can equip them with weak equivalences, which will be just subcategories. And then you have homotopy colimits in infinity categories. And the way to, in some sense, reconcile these two bullets, 1 and 2, is just to say that homotopy colimits compute infinity categorical colimits in the derived localization. So let me start with a small category C with weak equivalences W. I will think of these as homotopy theories, but you can also think of them as simply categories with some structure. Take the co-completion, pass to simplicial objects in the co-completion, and then choose some weak equivalences. And this should include pointwise, so for every C, the weak homotopy equivalences of simplicial sets, but you also want to include all maps between the representables that come from a weak equivalences that you had chosen in C, because you want to remember the weak equivalences in C. So this gives you pre-sheaves for homotopy theories. And in some sense, if you want to think of this as a category theorist, these are pro-arrows in the sense of formal category theory. So what do I mean by this is I can define bimodules, which is just a homotopical functor into this B hat, which is the construction that I gave in this previous slide. And you always have a bimodule associated to every homotopical functor. And every bimodule gives you a Quillen pair, which is unique up to a contractible space, such that this diagram is a natural weak equivalence. So you have a nerve for every bimodule, and you have you have Yoneda lemma essentially for homotopy theories, which just says that this nerve up to a contractible space of choices is the identity. So in some sense, you see that this construction gives you a lot of structure on homotopy theories. And I take this as a guiding principle to understand pre-sheaves, homotopy pre-sheaves in the enriched context, and then also enriched homotopy colimits. So over a point, you get spaces, the homotopy theory of spaces. So over a point, you must have something that behaves as spaces in the enriched context. You can call these V complexes or V spaces, whatever. So when people put model structures on simplicial objects, the first thing that we do is to look at the underlying simplicial sets. This is good, this is useful, but in this case, doesn't work. So what works is the following. For every simplicial object in V, you compose with mapping out of some object V in V. So instead of mapping out of the unit, you map out of every object. And you consider all these compositions. This composition is, of course, a simplicial set. And so you define a V fibration, I call it a V fibration, between simplicial objects in V as a map such that each one of these maps induced by this are confibrations of simplicial sets. This it must hold for every V in V, for every small V in V. Okay, so when I first considered this notion, I tried to look up if they already existed somewhere. Of course, for V equal to set, these are precisely the confibrations. In equivalent homotopy theory, and this I think is interesting. They are called fine or genuine vibrations, as opposed to the coarse or naive ones, which are those that instead forget the action. In homological algebra, these are called absolute vibrations. They were studied by Christensen and Hovey. And lastly, there is this paper by Gambino, Henry, Sattler, and Zumilo, where they prove the existence of a model structure on simplicial objects in V with vibrations that they call effective vibrations, which are precisely these V vibrations. And their paper is very nice, and they are able to prove the existence of a model structure under very, very weak assumptions on V. They don't even assume that all colimits exist. They have some motivation coming from constructive mathematics and homotopy type theory. So, but this slide is just to say that these V vibrations, they are found in nature in some sense. So yeah, I want to say something about this example, this equivalent example. So you take a group and you consider simplicial objects in G sets, and then if I want to interpret this model structure as the enriched cocompletion of homotopy cocompletion of a point, then Elmendorf theorem becomes the statement that the enriched homotopy cocompletion of a point is the same as the ordinary homotopy cocompletion of the category of orbits. So you need more generators if you don't use enriched homotopy colimits. So now there is this very important fact, which is due to Dagger over the category of sets. If you start with a one category C, you can build freely a model category generated by C in the same way as you build free modules. And Dagger and Shipley wanted to have this theorem over a billion groups. They have a paper on TAC, but they didn't manage to do so. They say it in their paper because they lacked the uniqueness part of the universal property. And it should be observed that Dagger and Shipley put on simplicial abelian groups the model structure where you forget the abelian group structure. And I would like this theorem to hold in the enriched context for general V. I need to use some definition of enriched model structure. The definition that I will use is one where you replace the weak factorization systems by enriched weak factorization systems. So the lifting properties are enriched lifting properties. These are found, for instance, in Reel's book on categorical homotopy theory. And this is different than the traditional notion of enriched model category, where you have a model structure on V. So I will say something at the end about this. So the enriched version of Dagger theorem is the following. You have a small V category C and an enriched diagram D into some enriched model category M in the sense of the previous slide. And then what happens is that you can extend D by what I call the realization of D. This realization will be V-enriched. It will be left Quillen, which if you don't know what it means, you can think of it as the notion of a junction between homotopy theories, or you can think of it as preserving homotopical limits. And the space of such extensions is contractible. And moreover, whenever you have a weak equivalence between diagrams, it will give you a weak equivalences between the realizations of the diagrams at every cofibrant object here. So this is the homotopy invariance of the homotopical limit in some sense. So now this gives you some corollaries. For instance, it gives you a way to have Dwyer-Kam mapping spaces in the enriched context. So just pick as a diagram just one object of M, then you will get a pair of adjoints. So you have a homotopically unique right Quillen V functor that in some sense gives you the mapping space out of M. And thinking of it as restricting on fibrant objects, it will land on Kam V complexes or V spaces, whatever. And so if I have a relative V category C, I want to see it inside its presheaves and then use the model structure on enriched presheaves to have the mapping spaces of the relative V category C. So in some sense, I'm seeing these as enriched infinity categories, and this can be made precise because there is, I mean, this doesn't really depend on what definition of enriched infinity category you use. You can apply some results of Gepper-Hausen and Luries to have that, to prove that the underlying infinity category of an enriched model category, in the sense that I said earlier, is enriched over the underlying infinity category of Kam V complexes. And so in some sense, this I would like to prove that enriched homotopy colimits give you a model for weighted colimits in enriched infinity categories, or at least in this fragment of enriched infinity categories. So then there are other properties of the homotopy theory of spaces. For instance, if you compute the space of enriched autoequivalences of this homotopy theory, you get that it's a contractible space, exactly as you want. And then another thing is this result of Joyal over sets is a fundamental result of Joyal. So if you take an internal category C in V with respect to the limit structure in V, so I'm assuming limits, and you can always define the nerve of C using pullbacks, and then this nerve will be what I call Kam V complex if and only if C is an internal groupoid in V. So now I want to say something about the more traditional notion of enriched homotopy colimit, where you fix a model structure on V, which is a natural thing to do, again. So the first person to study enriched homotopy colimits, at least in some sense to write a paper about them that I know of, is Shulman. There are also papers by Vokrinek and Lack and Rosicky that use enriched homotopy colimits or develop some theory. The common feature of all these works is, again, that they fix this model structure on V. But for instance, if you read Lack and Rosicky paper, they explain why they need to assume very strong properties on the model structure on V. For instance, that all objects are cofibrant. This is related to the need for an enriched cofibrant replacement, essentially. So in these last slides, I want to assume these good properties. I want to pick V, and I want to choose a model structure mu on V, which will be very good without going too much into technicalities. Let's just say it's very good. And in particular, all objects are cofibrant. So now take a look at this diagram. On the right, you have ordinary enriched presheaves on C. On the left, you have simplicial objects in enriched presheaves on C. And then you have here the projective model structure obtained from the model structure mu on V. This means that by the enriched dagger theorem, we get this realization functor, which I call norm, which depends on mu. And that makes this diagram commute up to weak equivalence. Now, if you take a look at this other diagram, on the right, pick a model structure which is enriched in the model structure mu on V. So this is the traditional definition of enriched model structure, which, if you don't know what it is, just think that the point is that the weighted colimit functor, the ordinary one, just from enriched category theory, becomes a left Quillen V functor when M is an enriched model structure. And so now you have this triangle, this upper triangle that commutes up to isomorphism because it just comes from ordinary enriched category theory. On the left, you have this triangle from the previous slide, which commutes up to weak equivalence. And then this composition will be, again, a left Quillen V functor. Then if I apply the enriched dagger theorem, I also get this realization of D. And by the uniqueness, I get that this must be Quillen homotopic. So you see that in some sense, if you define enriched homotopical limits using this realization factor, it will coincide with the traditional notion of enriched homotopical limit when you are weighting your colimits by the image of this functor norm, which depends on the model structure mu on V. So now to give the easiest possible example, let's take V equal to sets. Then what are enriched model structures over the trivial model structure on set? So mu is the trivial model structure on set. So M becomes a co-complete category. And then what I have is that this is just a tensor product of functors. But I still get this realization functor because this is still a model structure. Even if on set I have the trivial model structure is a co-complete category. So this is a model structure. I get this realization functor. And then I compose this, and the fact that these must be Quillen homotopic just means that they must be naturally isomorphic in this context because weak equivalences are just isomorphism. So then you see this last line says that if you compute the homotopical limit of D as the realization of a cofibril replacement of the point, this is isomorphic to the colimit of D weighted by the value of this cofibril replacement at this norm, which is just a point, which is then a colimit of D weighted by a point, which is precisely the colimit of the diagram D. So this is how you retrieve ordinary colimits as homotopy colimits for W equal to isomorphism. Something similar happens for enriched colimits. So this is how I get, in some sense, the requirements that I told you about at the beginning. And this is where I also conclude my talk. Thank you very much.
Thank you for the talk. So we have some time for questions. Of course, everybody's clapping silently.
So I have a question. So when it comes to level of generality, from what I understand, your work is more general than Rosicky and Luck, and then also the follow-up works of Rosicky, Luck, and Vokrinek, and the collaboration that they have also with Burke. So first of all, is this correct? And second, if it is more general, what are we getting? like what kind of things we can do with your technology that we could not do before. In particular, I'm interested in enrichment of a V over V equals cut and model structures given by natural homotopical structures. So I'm sure you understand the question.
Yes. So in some sense, the point is that I wanted to so asking what you get more when you want to compute homotopical limits, you pick whatever model is more convenient for you for the specific situation, because they all boils down to finding cofiber replacements and or finding cosimplicial resolution. So it really depends on the situation, and I cannot really say that in specific applications it would buy you something more. On the other hand, I think that this so my way of thinking is that when you start with categories with weak equivalences, so just one categories with weak equivalences, you get the enrichment over spaces that is given you as the underlying infinity category. It's not, does not come from enrichment over simplicial sets that you impose at first, right? And then you can, the way you see the mapping spaces of the relative categories by seeing it inside the projective model, the Busby localization of the projective model structure. So inside its homotopy presheaves. And the mapping spaces there, which exist because it's a model structure, compute the mapping spaces between the representables. So they allow you to see the category with weak equivalences as an infinity category. So then what if you want to do so for V categories with weak equivalences? Then the way to do so is to do what I said in some sense. You cannot do that with working with more restrictive definitions of enriched homotopical limits. So in some sense, my motivation was more of understanding all these various ways that you have and put them in some framework that retrieves all of them in some sense. And regarding cut, so if you take V equal to cut, then you have something like Elmendorf theorem, the same thing as happens as for G sets. So the underlying infinity category will be the infinity category of presheaves of spaces on connected categories. So what this is, I don't really know how to interpret this, but this is what happens for cut. It happens also for any locally connected topos, for example. So I don't know if I answered your questions or not.
I would have more comments, but I think the moderator would kill me. So I'm happy to call it a day.
Okay.
Thank you.
But I would like to hear your comments if you want to.
Yeah, sure. Maybe later. Absolutely.
And I have plenty of occasions to kill you even, so don't worry. Any other?
There's a question in the chat, Fosco.
Yes. So can you perform the same kind of constructions where delta op, comma v is representably given a kind of model structure using the Joyal model structure on simplicial sets rather than the Quillen model structure, i.e. with fibrations being isofibrations rather than confibrations?
What do you mean by performing these same kind of constructions? I mean, I don't know, because when you compute homotopical limits, you want, I mean, the homotopical completion of a point is spaces. It's not, I mean, I don't know if I don't really understand what you mean by this question. I guess that something interesting could be to see if, for example, if we have this, so if we have some enriched notion of complexes, then can we have some enriched notion of quasi-categories by considering simplicial objects in V? This is a good question, and there is some work by Arne Mertens that is, in fact, I talk a lot to him at CT because in some sense, this thing that I'm doing is related to his work. But he works in, but there are some points, because when you consider internal things, for instance, when you consider an internal category in V, if your base of enrichment is monoidal, then you will have two different notions of internal category, one with respect to limits and one with respect to the monoidal product. So Arne is working with respect to the monoidal product in V. So this introduces a lot of complications. And so, yeah, there is some, I don't know if this was your question, but yes, there is some relation with some notion of enriched quasi-category. So thank you for the question.